And now we, right.
Yes, unlike rooms in a regular conference, peers can actually just get rid of the room.
I can completely destroy the room, that's right.
Which you're probably not supposed to do in a regular building.
Well, they may be in the middle of the solution of the high TC problem.
Well, there you go.
Yeah.
Tough luck. Yeah.
Let's see. I think what we're going to do is I'm going to hand it over to you, Andrew, and you can take the introduction away, and off we go.
Okay, so welcome back. Let's start. Today we have the second talk from Johannes Lischner. He did his PhD at Cornell in the group of Professor Thomas Arias, then a postdoc at Berkeley, UC Berkeley, with Stephen Louis and Martin Cohen. Since 2014, he is in Imperial as a Royal Society University Fellow, Research Fellow at Department of Materials and Physics, and a senior lecturer in Department of Materials. So one of his current line of research interests, and this is not the only one, he has many other ones, is in the studies of electronic properties via DFT, density functional theory and first principles, perturbation theory, and classical force field methods in 2D materials like graphene, and particularly today's topic, twisted bilayer graphene, which he's now going to tell us more about. Johannes.
Okay, thank you very much, Andrew, for the kind introduction. Of course, I want to thank all the organizers of this wonderful conference to invite me back. As I alluded to on Monday, last year's talk was actually extremely important because it led to a new collaboration with Dmitry Efetov that I will sort of talk about in the end of my talk, that really sort of shed new light on the physics of this new material. As this is sort of the second part of a two-part seminar, I will be much briefer, of course, in the introduction, since I gave a lot of introduction into the topic on Monday. Let me see. Okay, so twisted bilayer graphene is of course a MOIRE material that you get by sort of putting two aligned graphene sheets on top of each other and then rotating the one with respect to the other one. And what emerges is this lovely MOIRE pattern where you have AA regions where the graphene sheets are perfectly on top of each other, and then AB or BA region where sort of the carbon atom from one are in the middle of the hexagons of the other ones. And so these regions form this emergent MOIRE pattern. One of the things that I think we as theorists should emphasize very heavily is that it was actually theory that predicted that this is an interesting system to look at. So in particular, it was a couple of groups, but the most prominent one was the group of Alan MacDonald and Bistritzer, who predicted in 2011 that this material should exhibit flat bands when you tune the twist angle to the so-called magic angle, which is around 1.1 degrees. So here I'm showing you again the evolution of the band structure. So this is the non-interacting tight binding band structure as a function of twist angle. And what you see is that the width of these flat bands, the width of these bands near the Fermi level, it shrinks and shrinks as you approach this magic angle. So here we're very close, and you can see these bands only have a width of, maybe 10 millielectron volts. But then if you go beyond to even smaller twist angles, it sort of opens up again. And of course, flat bands means slow electrons, and that means sort of the electrons have very little kinetic energy. And that in turn means that it is likely that electron-electron interactions are going to play a prominent role in this material. in the vicinity of the magic angle.
Johannes,
Now it took. Yep.
A question from Ignat Fiskovsky.
Go ahead.
Ignat, do you want to unmute and ask your question? No, maybe it's just on the chat. So the question is, why is the magic angle 1.05 and not 1.25 degrees?
I'm not saying it is. I'm not saying it's 1.05. And I'm not saying it's 1.25. I mean, it's sort of, I mean, sort of magic angle, the precise value depends on the parameters of your model. And sort of depending on who does the calculation and what he fits his models to, the magic angle is somewhere between 1 and 1.2 degree. Here I'm showing you just a bunch of band structures with the smallest bandwidth at 1.25, but the bandwidth will decrease as you go to a little smaller twist angle. That's all I'm saying here.
Okay, thank you.
Can I just also ask a follow-up question on this? Because if I understood from your previous talk, the size of the unit cell in each of these figures is different. So the scale of going from K to gamma is different. And so on, these are different wavelengths. So what exactly do you mean by comparing a flat band? Because I mean, it's very difficult to tell because the scale on the x-axis is different in each case.
You're absolutely right. You're absolutely right. But if you calculate the band velocity, it is still true that at the magic angle, the band velocity goes to 0, right? So if you turned off interlayer coupling and you calculated the band velocity as a function of twist angle, it would always be the same as that of graphene. But if you actually turn on interlayer hopping, you can see that the band velocity actually goes to 0 at the magic angle. So I'm talking about the slope of the band.
Okay, so really, so we can't necessarily see that from these figures, but you're telling us it does happen.
Exactly. Exactly. So I mean, I appreciate your point that the scale on the x-axis is changing, and that makes it a little harder to compare.
Okay,
that's true. Okay, right. So 2011 theory, a true theory prediction, and then it took experiment quite a few years to catch up. But eventually, 2018, the group at MIT of Pablo Llorillo Herrero was able to fabricate these very precisely aligned samples and measure transport properties. And indeed, there was interesting physics that they hypothesized to be related to electron interactions playing a dominant role, and in particular, at high elevated temperature that manifests itself as additional insulating states, which are these two here at minus and plus ns/2, which are not predicted by a band structure picture and therefore are sort of assigned as correlated insulator states as opposed to band insulator states. When you cool it down, what they also found was the emergence of superconducting domes on both sides of the MOT or correlated insulator states. And so they were able to make a phase diagram of carrier density versus temperature, which if you compared it to the high temperature cuprates, which are shown on the right here, this bears some remarkable similarities. And so a lot of people were intrigued, are still intrigued by this possibility of maybe understanding cuprate physics, well, through twisted bilayer graphene. But I guess one of the messages of my talk today is that you have to be careful. I mean, it might just be that, talking in biological terms, that twisted bilayer graphene and the cuprates are similar phenotype. So they look the same, but when you sort of look inside at the genetic makeup or the microscopic mechanisms that give rise to this phase diagram, it might be that they're different, right? And so that will be one of the main lines that I'll talk about in my talk today. So from a theory point of view, you could basically say the simple question that we have to answer is, what is the role of electron-electron interactions in this material? We understand, without electron-electron interactions, we essentially understand this material. All the complicated physics is associated with electron-electron interactions and possibly also other type of interactions like electron phonon. Now, it might be very tempting to sort of, jump into the middle and try to understand broken symmetry phases of this material. And historically, I have to admit, that's what I did. But recently, I've started to trace retrace my steps and decided to study electron-electron interactions in the normal state first. And I hope I can show you that there's a lot of interesting lessons to be learned in the normal state. So how do we study the normal state of twisted bilayer graphene? So by normal state, I mean either sort of the semi-metallic state when it's undoped or the metallic state when it's doped. And the theory that we have been using to describe electron-electron interactions can be described as an atomistic tight binding based Hartree theory. So what we do is we add to the non-interacting tight binding Hamiltonian that I discussed on Monday, we add a sort of interaction term, which is sort of a local, which can also be interpreted as a local on-site energy that depends on position. And this is the Hartree potential energy. When the Hartree potential energy is calculated from the density, so N of R is the electron density, N0 is a reference density, and a W is the fundamental interaction. And here I'm making the assumption that the fundamental interaction is just a 1 over R interaction that is screened by some background dielectric. So we were dealing with long-range interaction here, which is sort of what we would expect of a two-dimensional semi-metal like graphene. Let me also say that we need this reference density basically because we can only do periodic calculations on a neutral system. So somehow we have to compensate for these additional, if we want to study doped systems, we somehow have to put, some balancing charges. And in addition, we also want to avoid a double counting of interaction because the hopping parameters here are fitted to DFT, and the DFT already contains some Hartree interactions within itself. So we don't want to double count, and that we can achieve by subtracting an appropriate reference density. And so this is,
sorry,
yeah, go ahead.
There is a question from the chat from Yiping Huang. In this Hamiltonian, are you using fridge? What's fridge spinor type weight? Can you, Yiping, can you unmute yourself and ask a question?
Yes. I have a question. So when you write down this effective Hamiltonian, in principle, you need to write down some localized one-year orbital.
No.
Right?
I mean,
so
no. This is an atomistic Hamiltonian. Ci and Cj create PZ are the creation operators for PZ, atomistic PZ.
Oh, I see. Thank you.
So what we're dealing here is we're dealing with a mean field, a self-consistent mean field calculation in a very large Hilbert space. So we're dealing with 10,000 atoms unit cells. We're dealing with all the degrees of freedom, all the PZ orbitals, and solving this problem self-consistently. So computationally, this is quite intensive. So much harder to do than a simple atomistic tight binding calculation. But then we get band structures out of this mean field theory. And basically we get band structures as function of doping. So here we see, I'm showing you 4 different band structures. Nu is the number of electrons that have been added to each MOIRE unit cell. So here, 0 means neutral, and then 1, 2, 3 means 1, 2, 3 electrons have been added. Of course, the maximum you can add is 4 before you completely fill the flat conduction bands. And what you see here in the corresponding colors are the band structures of these doped materials. And now there's a couple of interesting observations that you can make from this band structure. In particular, what you see is that doping leads to a distortion of the band structure. The band structure becomes less electron hole symmetric than it is in the neutral system. In particular, what you see is the more electrons you add, the flatter the conduction band becomes, but on the other hand, the valence band become more dispersive. So actually the overall bandwidth doesn't change by that much, but sort of the bandwidth of the conduction band becomes smaller, and the bandwidth of the valence band becomes bigger as you dope electrons. Now we can also see what happens when we dope holes, and the opposite happens. So what happens is that the valence band gets flatter and flatter as I add more and more holes, while the conduction bands become more and more dispersive. So this is at a twist angle of 1.54 degrees, so it's a little ways off the magic angle. So why does this happen? Why does, I mean, if you just have tight binding, then of course you cannot capture the effect of, of doping on the band structure. So Hartree theory gives you sort of this qualitatively new effect. And basically, the reason why Hartree theory gives you this effect is because microscopically, we're dealing with an inhomogeneous material. So here I'm showing you the charge density of doped twisted bilayer graphene. So here I've added 3 electrons in the MOIRE cell. And what we know is that these carriers localize in the AA regions. So there's a large charge density in the AA regions. And then, of course, this charge density creates a Hartree potential. Now, this Hartree potential actually will push up any charge that is localized in the AA regions. And that's precisely what we see here. So let me try to go back. So the states at K are states that are localized in the AA regions, and they are essentially pushed up relative to the states at gamma, because the states at gamma are actually not localized in the AA regions. They have a ring-like shape. So by adding these extra electrons, we create this repulsive potential in the AA regions that pushes up states in the AA regions, and that sort of leads to this deformation of the band structure and the flattening of the conduction band. All right. Okay, and now that we have understood this effect, what's going on, we can study the band structure as a function of twist angle in this material. So here I'm showing you again the evolution of the electron dope band structure as a function of twist angle. 1.54 I've already shown you. Now let's go to maybe 1.2. You see something interesting is happening. The bands have gone very flat for nu equals 1, but then for nu equals 2, the conduction band has actually completely inverted. Right? So you get qualitative changes, not only deformations and distortions, but actually qualitative changes to the band structure. And the interesting thing is you get these extremely flat regions in the bands near gamma, right? So basically completely flat bands. And then if we look at 1.16, which is very close to the magic angle in our method. So you see the neutral band structure is basically very flat. And if we include now electron-electron interactions, we see that these Hartree interactions lead to a significant widening of the bands as a function of doping. And then as we go beyond the magic angle, so let's say theta 1.05, it starts going back to sort of a qualitative to the picture of 1.54 degree. So there are sort of very distinct new effects that you get already from a self-consistent Hartree approach. And these new effects, they raise some interesting questions. In particular, you could ask, what is really the magic angle now? What is really the magic angle if I take electron-electron interactions into account? The flat band width that people often talk about, that's just a proxy, really. I mean, what matters, if you think about weak coupling theory, is basically this density of states at the Fermi level, right? Or you could say what is more closely related to the density of states of the Fermi level is actually the width of, let's say, the doped band. So here I'm showing you now the width of the conduction bands of the electron doped system. And in contrast to the total bandwidth, which has this sort of very nice V shape, you see that if I look at only the conduction bandwidth, I get a much more complicated picture, right? So sometimes these minima, so here the different colors again describe different doping levels. So if I look at nu equals 3, you see my minimum, my smallest bandwidth is actually at an angle of 1.3, and then it increases again. Well, similar for nu equals 2, you see I'm getting sort of a couple of angles where I get very flat conduction bands. So this really asks the question, you know, is the magic angle as identified from band structure theory, is that really relevant to predict the twist angles where I should expect strong correlation phenomena? And I think, you know, the answer is probably not really. So now let's also look at the evolution of the whole dope twisted bilayer as function of twist angle. And what we see is something similar. So now the valence bands flatten, and at some twist angles, so here, for example, for nu equals -3, I get extremely flat valence band in the gamma region. And then as I go closer to the magic angle, I get this inversion of the band structure, which again is not predicted by non-interacting tight binding theory. So again, the key lesson is, of course, that, you know, analyzing the effect of electron-electron interactions in the normal state is quite relevant and gives us sort of new insights.
Before you go on, Sam has a question on chat. If I recall correctly, relaxation of the lattice has to be taken into account when working out the band structure. Does one have to consider further lattice movement when doping?
That is a very good question. And the answer is, in principle, yes. In practice, nobody has done that yet. So yeah, because basically what most people do is they use a classical force field to do the relaxations. And classical means that this force field doesn't know about electrons. So this, you know, so in principle, yes. In practice, we don't know how to do that. But it is a very good question. So on Monday, I was asked about how one could sort of ascertain that these flat bands are real, which of course is a good question since we're basically obsessing about them. And of course, the most direct probe of the band structure is RPES. And quite recently, there was a group that did a nano RPES experiment on twisted bilayer graphene at the magic angle. And this is their result. And what you see here is, of course, on the y-axis, you get to see a very big energy scale from 0 to 1. And well, this red arrow denotes the flat bands. And well, I mean, the only thing you can really say is, yes, there are probably flat bands, but that's all you can really say from this picture, which is, you know, is of course a comforting knowledge that, you know, they do exist. But from RPES, we can't really learn much about the flat band dispersion. A much more useful technique is scanning tunneling microscopy or scanning tunneling spectroscopy, STM or STS. And that has been done by a couple of experimental groups. So here I'm showing you a spectrum from Kurelsky et al. So this is the Columbia group, where on the x-axis is the energy in milli-electron volts. You can see you have very fine resolution. And then on the y-axis, well, is what they call the local density of states. A more accurate description is it's the tunneling spectrum. And what you see is that there are some very pronounced peaks in the AA regions. And then, well, there are some relatively minor peaks in the AB region. So most people sort of focus on the AA regions. So let's understand this results using our band structure. So here's again the band structure of twisted bilayer graphene. And from the band structure, we can, of course, calculate the local density of states. And this is done here. And so you see that the local density of states indeed has two peaks. And these peaks actually derive from states near the endpoint of the unit cell. So this is, of course, a point where you have a saddle point in the band structure. So what you see here is a well-known Van Hoff singularity. And since the states at the endpoint are mostly localized in the AA regions, you get a big LDOS in the AA region and just a relatively minor one in the AB region. So this is basically consistent with theory, and what it tells you is that the separation of the Van Hoff singularities of these peaks is basically a reflection of, you know, the band structure. So that's something that is sort of very important to study. Now, what they also do is a very detailed study as a function of doping, right? Because you can dope twisted bilayer graphene very easily using the electric field effect in a transistor setup. And so here on the left-hand side, you see as a function of doping level. So all of these are spectra, 4 different doping levels, right? And on the x-axis is the energy in millielectron volts. Now, of course, you have to look at this for quite some time to digest this wealth of information. But the main points are, if we look at sort of the extrema, right? So let's look at the bottom here, and what we see is basically the Van Hoff singularity close to 0, and 0 is, of course, the Fermi level is quite sharp, while the Van Hoff singularity that's further from the Fermi level is broader. And as we go to the very top, we see that it has switched, right? So here now the left Van Hoff singularity is sharper, and the one on the right is a little bit broader. If we look at the dispersion of these Fermi velocities, we can also see that there is a change in their distance as a function of doping level. Now, on the right-hand side is a zoom in, and what they sort of pointing out in this graph is that sometimes you actually see sort of a breaking up of the Van Hoff singularity, and you get a sort of double peak. And this double peak is actually interpreted as a signature of a broken symmetry state. So you could explain this double peak, for example, by the system becoming magnetic.
Johannes, there's a question on chat.
Yeah, go ahead.
It's quite a long one. If one thinks naively, the MOIRE unit cell size would increase as twist angle decreases, and the bandwidth would be inverse proportional to the unit cell size. This naive picture seems to work for the angles larger than 1 degree, but not for smaller angles. Is there a simple answer for that? This is from Sun Sup Lee.
Okay, so I think I might kind of defer this question to the end because it's not directly related to the discussion at hand. Is that okay? Because I mean, I think I have to think about it more than I can do right now. So apologies. I think let's discuss this after the talk, if that's okay. So okay, so let me stick with the discussion of the STM spectra for now, for fixed twist angle. So here I'm showing you an STM result from a different group. So this is the group of Ali Yazdani in Princeton. And so here they're showing you basically the same thing, but as a heat map. So they're showing you as a function of doping, the evolution of the tunneling spectrum. And what you see here is basically this first region where you see the sort of linear dispersion. That's when the flat bands are sort of completely filled, and you get sort of 2 peaks that just move basically because the Fermi level is changing. Then, however, once the Fermi level hits the high energy Van Hoff singularity, basically the spectrum stops moving. And what this means is you get Fermi level pinning. What is very interesting interesting though is that when this Fermi level pinning happens, if you look at the place if you look at the spectrum, the Van Hove singularity seems to completely disappear in this measurement. So that's very strange. So, and then the Fermi level stays pinned for a while until you're sort of, you move into sort of close to the charge neutrality point, which is sort of this region here. And then the spectrum becomes very symmetric and is unpinned. Then again, there's a short region of pinning when the Fermi level hits the other Van Hove singularity. And then again, you have completely emptied out the flat bands, and you again get a dispersive, tunneling spectrum. And finally, I want to show you a measurement from the group of Najperg at Caltech, which sees something quite similar. So again, a dispersive tunneling spectrum when the flat bands are completely filled, then you get Fermi level pinning, then again, dispersion near the charge neutrality point, another region of pinning, and then again, dispersion. So, so this is sort of the state of the experimental knowledge of the normal state. So let's now try to compare this to our calculations. But before we do that, we can also look at the twist angle dependence of the tunneling spectrum. So, so here you see basically the result from the Columbia group for 5 different twist angles. And as you would expect, these Fermi, these Van Hove singularities keep sort of approaching, but weirdly, they keep doing that. So based on the band structure picture, at some point beyond the magic angle, you would expect that they sort of separate again, but this doesn't seem to happen in this experiment. So this is, I think, a mystery. Anyway, so now I want to compare these measurements to our atomistic Hartree theory calculation. And so I'm showing you now the local densities of states for 3 different twist angles, 1.5, 1.4, 1.2. So 1.2 is, of course, the one quite close to the magic angle. And as a function of energy with respect to the Fermi level. So 0 is the Fermi level. And basically, I'm showing you sort of, again, for 7 different doping levels. So nu is, again, the number of electrons that you have added or removed from the material. Now, let's start with 1.5, which is quite far from the magic angle. And what we see is, well, we do get these Van Hove singularities, but they're sort of quite similar. So there's not a lot of asymmetry in these Van Hove singularities. And you see that they sort of more or less readily move past the Fermi level. So here we don't see any Fermi level pinning. Now, if we look at 1.4, you see already this is starting to change. So if I look at the red curve, nu equals -3, you see that the Van Hove singularities are very asymmetric. And this electron-hole asymmetry is, of course, caused by Hartree interactions and is in agreement with experiment. And what you also see is now the Van Hove singularities don't move very readily past the Fermi level. So you start to see Fermi level pinning in the calculation as well. And again, that gets even more pronounced when you go very close to the magic angle. You see strong asymmetries, strong Fermi level pinnings, and you start to see some very strange shapes in the local density of states. So the Van Hove singularities acquire some definite structure, and sometimes the structure looks a lot like a double peak. So this sort of raises then some questions about the interpretation of the experiment, basically where this double peak was interpreted as a broken symmetry, as a signature of a broken symmetry. But here I'm showing you that even in the normal state, the Van Hove singularity can acquire sort of non-trivial structure in the vicinity of the magic angle. Okay, so this was all I wanted to say about the normal state, and I hope I've shown you that there's already a lot of interesting stuff going on in the normal state before we start thinking about breaking any symmetries thinking about sort of magnetism or superconductivity or any of that. But so now in the second part of my talk, though, I want to do just that and see if we can sort of what we can learn about broken symmetry states. Now, sort of the standard way people study broken symmetry states is using a model Hamiltonian.
Piers just had a question in the chat, so maybe it'd be good to take that before you move on.
Go ahead.
So Piers, do you want to state your question? Or?
Unmute. Yeah, fascinating talk. I like the way you can get the Fermi, the pinning of the levels to the Fermi surface, Fermi energy. Can you tell us a little bit more? Is there a simple criteria for when the Coulomb interaction compared with the bandwidth? Is that the criteria for when you get the pinning, when the Coulomb interaction exceeds the MOIRE bandwidth by a certain amount? Can you give some quality?
Yes. So I mean, what's happening is so what you get is essentially this Hartree potential, right? And that Hartree potential has a certain variation throughout the unit cell, right? And so you can ask, what is sort of the difference of the Hartree potential in the center of the AA region and versus the in the AV region, right? So this is the relevant scale that the interaction gives you, the variation of the Hartree potential throughout the unit cell, and that you have to compare with the bandwidth essentially. And okay. For 1.5, this is a small effect. But for 1.2, this is a big effect.
Thank you very much. Thank you, Johannes.
Okay. There's also a question from Jean.
Sorry, I'm also very fascinated by this data. Question. So can you attribute this double splitting of your one-half similarity to anything? I mean, in principle, if you allow it, the Hartree theory can also capture some sort of a symmetry breaking. It not?
Well, I mean, yes. I mean, symmetry breaking is one explanation, yes. But what I'm telling you is you don't have to invoke it if you don't want to. Basically, let me scroll to the band structure. Basically, what we find is, well, I mean, I told you that the Van Hove singularity is caused by states, by the stationary point, by the stationary band near the endpoint. But yes. Now, what you can get is sort of this flat region near gamma. So this is a Hartree effect that you don't get in tight binding. And this flat region, you see, is very close to where the band is at M, but it doesn't have to be exactly the same. So if this flat region near gamma is slightly offset from the band, from the value of the band at M, then you can get two peaks which are not precisely at the same energy.
I see. So it's some sort of a momentum-dependent Hartree.
So again, it's
like a momentum-dependent shift of the like a momentum-dependent potential.
A momentum-dependent potential. Yeah. So exactly. So the Hartree potential leads to this complicated deformation of the band structure, and there's not a simple shift. Yeah. And of course, fundamentally, all I'm saying is, you know, the charge density is inhomogeneous, and that makes it complicated.
I also have one quick question before you move on, if that's okay.
Yeah.
About the normal state, that when graphene and bilayer graphene were first made, there was a lot of excitement about the Dirac-Cohns and Berry phase, and which gave rise to anomalous transport and everything. And I think you told us that these are still hexagonal moire cells, just a lot bigger. So do you still expect them to have Dirac-Cohn-like physics and all this anomalous behavior? And has anybody tried measuring this in the normal state?
Yes, so you would say there's still anomalous behavior going on, and there is sort of a lot of people thinking about the topological properties of this material, and sort of things like orbital magnetization have been predicted, and there's experimental work also by Dmitry Efetov. So all of these things, there are similar questions being asked. The topological properties are a little different because you know, I mean, the key point is that the two K and K prime points of the mini Brion zone, of the MOIRE Brion zone, actually derive from the same K point of the graphene sheet. So that sort of gives rise to a difference in the topological properties, but there are definitely some aspects in that direction. It's just I can't very competently comment on these things.
Okay, thanks.
Okay, let's see. So we wanted to talk about electron-electron interactions and broken symmetry phases, and the framework that many people sort of, the traditional framework, let's say for this, is studying some sort of Hubbard Hamiltonian, which of course might be suggestive because of the apparent similarity to the cuprates. So if you're sort of saying, okay, let me try to describe twisted bilayer graphene by a Hubbard model, you still have sort of the question, okay, but what are the parameters? What is T? What is U? And in particular, what we know about the Hubbard model is it's the ratio of U over T that determines where sort of broken symmetry phases are expected. So as I described on Monday, you can calculate T and U from basically by generating Wannier functions and then evaluating sort of the matrix element of the Hamiltonian, the non-interacting Hamiltonian end of your interaction. So I won't go into detail. I'll just show you the results. So here on the left-hand side, I'm showing you the value of the Hubbard interaction, the on-side U, as a function of twist angle. And I think we've assumed a sort of background dielectric of 4 or 5 here to basically say that the twisted bilayer graphene is sandwiched by hexagonal boron nitride slabs. And what you see is that the Hubbard parameter is sort of on the order of, let's say, 60 to 100 MeV, and it sort of becomes smaller as the twist angle decreases. And that's just a reflection of the fact that the Wannier functions also scale with the size of the MOIRE unit cell, so they become more and more delocalized as the unit cell grows, and that means sort of that leads to a reduction of U. But then on the other hand, we know that the hopping is sort of proportional to the bandwidth, and so here I'm showing you the bandwidth as a function of twist angle, and of course that goes to 0 at the magic angle, and so then we would expect, of course, if we calculate U over T, that at the magic angle, basically the thing blows up, and it does. But sort of the question is, what does it mean? So obviously, it's an interesting question because very close to the magic angle, we're very much in the strong coupling regime. If we go further, maybe weak coupling approaches can be used. But in terms of the phase diagram, we have to compare sort of the value of U over T to the critical U over T where a phase transition happens. Now, of course, to say what the critical U over T is, you have to have a theory of what the broken symmetry phase actually is, and then you have to calculate the critical U over T. We haven't done that, but what we've sort of said is, what you would expect is that there is a phase transition when U over T is of the order of 1. And basically, we know from quantum Monte Carlo calculations of the untwisted bilayer and from some, RPA calculations of the spin susceptibility that you would expect phase transitions, at least to magnetic phases, to appear roughly at U over T of about 2. So here, this horizontal line is U over T equals 2. And while, you have to take that with sort of a grain of salt, what you see here is that the actual U over T is always above this critical line. And what this means is you would expect basically broken symmetry phases over a very large twist angle, a very large twist angle window, which is not what they see in experiments. So there must be problem here.
Can I ask a quick clarification question? These U and T parameters you're talking about, is that with or without the Hartree potential?
So this is, so we start with a tight binding band structure, so without Hartree, and then basically Coulomb interactions are included through the calculation of U.
Right. So you're back to the bare band structure to get the U. Okay. So there's no issue.
So T doesn't know about interactions at this point. Yes. Yeah. So I mean, chronologically, that work actually came first, as I hinted at. Okay. So there must be something wrong, because this prediction is in disagreement with experiment. And of course, obviously, what's wrong is that we're dealing here with a two-dimensional semi-metal, and we know that these materials have long-range interactions. So what we can then look at are sort of extended Hubbard parameters. So here we're calculating the matrix element of the interaction between Wannier functions in different MOIRE unit cells. And here I'm showing you basically how these Hubbard parameters decay as a function of distance. And the black line is just the bare Coulomb interaction, right? So here I'm showing you results for 3 different twist angles, and you see after 100 angstrom or 10 nanometer, they all fall on just the 1/r line. So basically what this tells you is, you should really look at the long-range interactions. Just on-site Hubbard is not going to be good enough. So then, of course, how do you deal with a long-range Hubbard model with long-range interactions? Well, I mean, the elegant answer is you map it onto a short-range Hubbard model. And that has been done, for example, by Schüler and co-workers in this paper. And basically what they're saying is you can map a long-range interaction, a Hamiltonian with a long-range interaction onto a short-range Hubbard model by defining an effective U, which is basically the difference of the on-site Hubbard and the nearest neighbor Hubbard parameter. And basically what this says is that if you look at these graphs down here, is the energy cost of going from a doubly occupied to two singly occupied orbitals is not U, because when the atoms are sort of on neighboring sites, you still have an energy cost of V, than the nearest neighbor interaction. So the relevant energy scale is the difference between the on-site and the nearest neighbor Hubbard parameter, and this is precisely the definition of U star. So so now, of course, we can easily calculate U star from our extended Hubbard parameters, and when we plot U star over T, we get this red line, and you see now this red line is only in a small twist angle window above the critical U over T, which is in much better agreement with experiment, which only see strong correlation phenomena, in a small twist angle window close to the magic angle. Okay, so next, of course, I want to talk about another effect of long-range interaction, and that is screening. And this is particularly interesting because screening is fundamentally different in a two-dimensional material than in a three-dimensional material. And actually, there are new sort of control knobs in a two-dimensional material that we simply don't have in 3 dimensions. So there are things that you can do to twisted bilayer graphene that you couldn't do to the cuprates. And one thing that you can very easily do is what we call device engineering. So this means you can change the interactions between electrons in the twisted bilayer graphene by sort of changing the environment in which the twisted bilayer sits. So here you see a typical device setup, and well, the electrons, of course, feel the presence of the boron nitride substrate, which is a dielectric, but then they can also feel the presence of the metallic gates. And so basically the presence of these metallic gates through the well-known image charge interaction can sort of drastically modify the interaction between electrons in the graphene. And this is, of course, something that can be tested experimentally but something you couldn't do, for example. So you can't play with the electron-electron interaction in the cuprates in that way. So here I'm showing you then the extended Hubbard parameters as a function of distance for sort of the situation where you have metallic screening. And you see it looks very much different from a 1/r, so they decay much more quickly. So this is for a separation of 10 nanometers. So we assume that the boron nitride is 10 nanometers thick, which is of course quite thin. So now we can also study, so we can play this game even more. We can study how things depend on the thickness of the boron nitride layer. So here I'm showing you the on-site Hubbard parameter as a function of zeta, which is the thickness of the boron nitride. And you see, well, maybe not surprisingly, as the metallic gate gets closer and closer to the bilayer, there's more and more screening, and as a consequence, the Hubbard parameter gets smaller and smaller. So then you could say, okay, so this means the material gets is less strongly correlated if you sort of make a zeta small. But we have to be careful, right? We just said the on-site Hubbard is not enough. We need to look at U star because interactions are long-ranged. Now, U star is more complicated because it also involves the nearest neighbor Hubbard term, and sort of there's a question basically if the nearest neighbor Hubbard interaction decreases much more quickly than the on-site, then it's possible in principle that the effective U increases as you decrease zeta. Now this doesn't seem to happen, and this is sort of something that's very special to twisted bilayer graphene, that in fact the effective U star also decreases. So I'm always somehow surprised that people do not find this finding surprising, but it actually is surprising that U star has the same behavior as U. Now we can now try to map out the phase diagram of twisted bilayer graphene as a function of the thickness of the boron nitride spacer layer. So to do that, basically what we need is some information about what the relevant phases are and what the corresponding critical values of U star over T are. And we take that information from the study here, Klebel and Honerkamp, who have analyzed basically the spin susceptibility of twisted bilayer graphene as a function of U. And so they get a phase diagram, which is shown on the left here, where they see where the squares denote anti-ferromagnetic insulators and the circles denote ferromagnetic insulators. So, and on the right-hand side, you see the corresponding critical values as a function of temperature. So this is not very important. And basically, we use this information then to construct these phase diagrams. So these are phase diagrams where on the x-axis you have the value of the twist angle relative to the magic angle. And on the y-axis, you have basically the thickness of the boron nitride layer. And so these three graphs correspond to three different doping levels. Now, how should you interpret these graphs? So, okay, so let's say we're at -2 electron doping, and we have a sample that is sort of -0.05 away from the magic angle. So we're sort of going up and down here. And what this tells you is basically, as you start from a very thick boron nitride layer, you have a broken symmetry phase. And as you sort of go down, as you go to a very thin boron nitride layer, something like 2.5 nanometers, your system goes from the broken symmetry state back to the metallic normal state. Now, this is of course something that can be tested experimentally. And this is now where I'm going back to last year, where I basically showed in my talk that, you know, by sort of by controlling the thickness of the boron nitride, you could potentially change the phase diagram. And there was an experimentalist in the audience, Dmitry Efektov, who basically said, well, this is something we can test. So, and here is his measurement. So he actually made 3 different samples with 3 different boron nitride thicknesses. So D3 has a boron nitride thickness of 12.5 nanometers. D2 has a boron nitride thickness of 10 nanometers. And then D1 has a boron thickness of 7 nanometers. And for each of these, he did a transport measurement and sort of figured out the phase diagram as a function of doping on the x-axis and temperature on the y-axis. Now, for the thick boron nitride layer, which is device D3, you get a phase diagram that looks very much like the one we've seen before, where you get sort of multiple correlated insulator states at integer fillings, and then between these correlated insulator states, there are a bunch of superconducting domes. But you see that the phase diagram changes quite dramatically as you go to a spacer layer of only 10 nanometer thickness. You see some of these correlated insulator states start to disappear. And finally, as you go to 7 nanometers, almost all of them have disappeared. So there's a bit of a signature here. And you see that the phase space of the correlated insulator states seems to be taken up by the superconducting domes. Now, this is, of course, very interesting, because what it tells us that, you know, that this material might, after all, be very different from the cuprates. So the cuprates, of course, the dominant view is that the superconducting states is very closely related to the correlated insulator state. In particular, what many people think is that spin fluctuations that are inherited from the antiferromagnetic parent state give rise to the Cooper pairing. So correlated insulator states and superconducting states are strongly linked. But here you see this doesn't seem to be the case. Here you can, so that the correlated insulator state can completely disappear and the superconducting states can become stronger. So it seems like, you know, we have to, you know, open our minds to the possibility that, after all, these might be very, very, very different mechanisms that are at play in these well, clearly very different types of materials. Now, I haven't said much about superconductivity, but so now, of course, there's a big debate about, you know, what now is the mechanism of superconductivity. So sort of, if you're sort of used to the cuprates, then we think that there's a magnetic, sort of a spin fluctuation glue that gives rise to Cooper pairing. But of course, there's also a big community who believes that it might actually be just a traditional picture. It might just be phonons, because we know that in some materials like the buckyballs, phonons can give rise to relatively high temperature superconductivity. And after all, we're only talking about transition temperatures of about 1 Kelvin. So now I guess the situation is currently, you know, there are these 2 camps, and well, every camp predicts, each camp predicts a transition temperature of 1 Kelvin. So it's very hard to sort of say who's right.
A brief interruption, sorry.
Yeah.
There's a chat question from Ignat Fiakovsky. Sorry for a naive question, but integer filling is actually fractional if counted in terms of the completely full band?
Yes, so I mean, by integer filling, I mean, if you count the number of electrons per MOIRE cell. So you can put up to 4 electrons into the bands or remove 4 electrons. So by integer, I mean 1, 2, 3, 4. Okay. So it's just, yeah, I mean, it can be confusing, I agree.
There's also a question from Sentil.
Yeah, so I actually have 2 questions. So the first is about the role of inhomogeneity. You know, it's easy to get an insulator if it's easy to miss the insulator. You just need some percolating metallic part, right?
Sure.
So for example, you know, all these devices have twist angle disorder and other kinds of things. So is that something you should worry about?
Certainly. I mean, you certainly have to worry about these things. I mean, I mean, yes, there's certainly room for missing these. I mean, these are what I would argue are the best, the most homogeneous samples that have ever been made, because you know, Efetov has these recipes for sort of creating very highly twist angle homogeneous materials. But of course, we have to keep our minds open to this possibility.
Yeah. So the related question is that you know, as I assumed, you know, there's this paper from Brown University where they were able to do the same screening using you know, ordinary bilayer graphene located just 3 nanometers away, and because the density of states in bilayer graphene can be controlled electrically, they're able to, in the same device, turn on or turn off the screening. Okay. And then they don't see that the correlated insulator disappears at all when they turn on the screen, even though it's only 3 nanometers away.
Yeah, I mean, yeah. So I mean, you know, inhomogeneity among different samples is a problem, right? And I mean, another thing what you could argue is there are small differences in the twist angle, and what sort of we had long discussions is these small differences in the twist angle, are they more important than the small differences in the spacer layer? So it is a good comment. Yes, I mean, it's yeah. I don't know a good answer to this, but
it seems as though you know, different experiments give different answers on this issue of screening, right? So so what's actually going on? What's the robust conclusion according to you that we should draw?
Well, I mean, I think the key thing, I mean, I don't want to conclude anything at this point. I think it's too early to conclude. I think we need more samples and better controlled samples and see what measurements are. I think concluding anything too firmly at this point is too early. I mean, I think, but what I can tell you is, you know, I mean, these things are in agreement with what we expect based on these sort of detailed microscopic calculations that we can do. And you know, I mean, that's of course something that might give some confidence that, you know, if you do the calculation, you would expect, you predict similar trends. But,
so then somehow the Brown experiment, if you redid your calculation, in that case, you should predict the opposite. Is that the expectation?
If I redid my calculation, I would get the opposite. I don't follow.
Saying that, you know, these experiments use a bilayer graphene as the screening gate, right? So they don't find the destruction of the correlated insulator. There's a slight change of gap, but no dramatic suppression, even though the screening should be much more efficient in that case. Because there, you know, not making a new device each time. Right? Just the same device in situ, you're turning on or turning off the screening. And then the correlated insulator is still there. Right? So yeah, maybe that's a case where perhaps if you redid the theory in that case, it may be interesting to see whether you predict the opposite of what you predict.
Okay, it's a fair point. I mean, to be honest, I haven't. I mean, I've seen that paper. I haven't thought too deeply about it. But I mean, I do take your point.
All right, thanks. That's all.
So Yasha Komijani has a question that's kind of related, I guess. In the data, it seems the superconductivity gets weak with reducing the boron nitride thickness, and then strong again in the D1 sample. How significant is this with respect to sample variation?
Yeah, that's what I've been saying. Yes, I mean, there is some. I mean, we already know that. I mean, from the initial data from the MIT group, that sample to sample variation is significant when it comes to transition temperatures. You can easily get from 0.1 to 2 Kelvin. So you know, it's hard to sort of separate out the sample to sample variation in this case. And yeah, it's a fair point. Yeah, I mean, I guess what could be said, and I guess something that Efetov said in last year's conference, how many samples are, how many superconducting twisted bilayer samples are there in the world? And the answer is maybe 20 or something of that order of magnitude. So it's just not many. It's just not many samples around, and each of them are slightly different. Okay, so
just a little note. We are now at the hour, or roughly. So we've got another 25 minutes or so of well, question time. But let's.
Yeah, I have 5 more minutes.
Okay, excellent.
And, yeah, so there's just one final topic that I wanted to show, and then I'm done. And the last topic is okay. So I was just about to set it up, and sort of I've told you about these two camps: phonon mediated superconductivity and spin fluctuation mediated superconductivity. And well, we'll see. Well, they'll probably keep arguing for a while. I'm not going to say which one I sort of believe more. I mean, what I want to do is I want to sort of broaden the discussion a little bit and show you maybe yet another mechanism that can give rise to superconductivity. And so we came across this mechanism more or less by accident, because what we did is we were studying internal screening, right? So far I've told you about the role of external screening, but of course, you know, the electrons within the graphene also have the ability to rearrange themselves. And well, you can calculate this, and we did this using the random phase approximation. You calculate the dielectric constant, and to do that, you have to calculate the polarizability, which is given as a sum of all transitions from occupied to unoccupied bands. So here I'm showing you the polarizability as a function of wave vector and for 4 different twist angles. And you see, if you're far from the magic angle, you get something that's more or less linear, which is precisely what you would expect from graphene. But as you approach the magic angle, you get a very pronounced bump. And well, this bump is of course just a reflection of the renormalization of the Fermi velocity close to the magic angle. Now, from so this gives us the polarizability and then also the dielectric constant. And from the dielectric constant, I can calculate the screen interaction. And here I'm showing you the screen interaction as a function of position. So this is the screen interaction between 2 electrons. And what you see very far from the magic angle, so let's see the blue curve, basically what this says is we have a repulsive interaction, like, you know, we would expect between electrons. Now, as we go closer and closer to the magic angle, though, you see that at some point, sort of around 1.4 degree, the effective interaction actually becomes attractive between 2 electrons. And so this is a purely electronic interaction. It's not spin mediated, it's basically a polarization effect. Now you might say, okay, I mean, you know, attractive interactions are actually not something new. Every material has attractive interactions, every metal, and the reason is, of course, Friedel oscillations. So Friedel oscillation is, of course, an oscillation in real space that is caused by the discontinuity of the Fermi Dirac distribution in K-space. And so every metal, when you calculate the effective interaction from internal screening, has sort of attractive regions. But this is not it, because here we're dealing with a semi-metal, right? So this is undoped graphene, and in a semi-metal, there's no discontinuity in K-space. So here we really wouldn't expect Friedel oscillations to be observable. Now the reason, and it is in fact a different reason that gives rise to attractive interactions. And the reason is there is a discontinuity in K-space, but it doesn't derive from the Fermi distribution. It derives from the discontinuous behavior of the band velocity. So what we know is that the band velocity is very strongly renormalized for low energy bands, but then for high energy bands, the high energy bands just have the unrenormalized graphene Fermi velocity. So it's this discontinuity of the Fermi velocity or the band velocity that when you Fourier transform it to real space gives you attractive interactions. And now the question is, can these attractive interactions lead to a Cooper pairing, for example? Well, I mean, we don't know. We haven't done the calculation. I found it interesting to see that actually, well, I mean, it is quite well known that Friedel oscillations can give rise to superconductivity. And this is precisely what motivated Kohn and Luttinger in their famous 1965 paper. So if you read sort of the introduction, what they say is, it's very well known that there is an oscillatory potential in metals. And basically they want to see if these oscillations arising from Friedel oscillations can give rise to Cooper pairing. And the answer, of course, is affirmative. Now, the interesting thing is, though, when you hear about the Kohn and Luttinger superconductivity, most frequently you think about spin fluctuations. At least that's what I did before I read this paper. And the answer is in these Feynman diagrams. So this is the Feynman diagram that gives rise to Friedel oscillations. So this has the polarization bubble. But Kohn and Luttinger, of course, realized that they have to be consistent and take into account all Feynman diagrams at second order. And these additional diagrams are sort of those associated with T matrices and spin fluctuations. And that's sort of then what got well known in the context of the cuprates. But basically, the bottom line is that Friedel oscillations can give rise to superconductivity. And so there seems to be a reason to hope that these new type of oscillations that we have discovered could also potentially give rise to superconductivity in twisted bilayer graphene. So with that, I'm done after all.
Okay.
So let me just summarize very briefly. So I've shown you basically the importance of long-range interactions in the normal state. I've shown you that there are new opportunities to probe electron correlations in 2 dimensions, which are absent in let's say, the 3-dimensional cuprates. We have to, I think, some experiments, even though it's very debatable, and there are different experiments that come to slightly different conclusions, we have to keep our mind open to the fact that these materials are different from the cuprates. And finally, I've talked to you about internal screening and the possibility that this might give rise to a polarization glue. Now, the work has, of course, been done not by me most of the time, but by a very bright PhD student, Zachary Goodwin, and by a postdoc in my group, Valerio Vitale. I also want to acknowledge my longtime collaborator, Arash Mustafi, who is sort of an expert at Wannier functions, and of course, Dmitry Efetov for a very fruitful collaboration. So thank you for your attention.
So let's thank the speaker first and unmute. Okay. Piers has already gotten some questions in the chat.
I'll ask it. Yes, you had this fascinating peak in the polarizability function, the bubble, and it had a very characteristic wave vector where it was maximum. What determines that wave vector, and what is the associated length scale?
Okay, so the length scale I can show you. So you see these minima, they are sort of, so these little stubs here, they denote the size of the MOIRE unit cell for the different twist angles. So this is a minimum that occurs within a MOIRE cell. So we were talking about length scales of 30 angstrom, 3 nanometers. So, you know, a fraction of the MOIRE length scale. What determines this peak? What determines the position of this? That's a good question. So of course it has to do with sort of, I mean, I'm thinking of this more in energy space because the low energy bands are renormalized and the high energy bands are not. I guess energies can be mapped onto momenta just by, you know, velocity times k. But yeah, I mean, I don't have a very good answer right off the top of my head.
Because it's clearly selecting some Q
I'll
vector,
think
and
about
I'd like to have a physical feeling for where it's coming from.
Yeah, that's a good question. So basically, it's at small Q vectors, right? You're probing transitions. You're probing transitions. I guess I'm arguing that at small Q, you're probing transitions between the flat bands, and at large Q, the transitions between non-flat bands become dominant. I guess that's what I'm arguing.
Mm-hmm. Okay, thank you.
I'll think about it. I hope I can cook up a better answer than this.
Okay, so there was a question previously that you said you're going to defer till the end of the talk.
All right.
Yeah. I don't know if you can find the chat. Let me find it.
Can just ask it.
I'll speak up. So I asked if I understood naively, when I decrease the twisted angle, then the unit cell size would increase because wire size would scale up, and then bandwidth would inverse proportional to the unit cell size. So that's my naive understanding. And it seems that it's roughly true when the angle is larger than 1 or 2 or something. But it seems that there is a minimum around 1, and then it goes up again. I'm talking about the bandwidth goes up again. So is there a simple answer why it shows such kind of...
Yeah, so okay, so now I understand a little bit better. So the answer to your question is at twist angles larger than 2, basically you don't renormalize your Fermi velocity, right? So at twist angles larger than 2 degrees, the Fermi velocity is the same as if you have them, it's basically, it doesn't depend on twist angle, and therefore it's your geometric argument is perfectly fine. However, at smaller twist angles, the interlayer interaction does renormalize the Fermi velocity, and that's why your rescaling breaks down.
Okay, I see. Thank you.
Any other questions? I can't see anyone with a hand up now, nor in the chat. I want to point out to the students that Johannes unfortunately can't make the student-led session after this. Okay, so if you have questions, you should ask now. There won't be an opportunity later.
So can I just ask a very general question then, if there's nothing else? Where did you see these MOIRE materials going next?
Well, I mean, you don't have to be a sort of a seer to say that it's definitely going into the TMD region. So I think that's sort of the next big thing too. And the TMDs, of course, have a lot of interesting, well, you have a much bigger material space of different systems. And you have new physics, you have sort of strong spin orbit coupling, you have interesting optical physics, you have excitonic physics, you have sort of, the TMDs have sort of this intrinsic electronics. So there's like a huge new playground that will very soon be very prominent, I believe. So.
We've got a few more questions now. Gunnar, you have a question. Gunnar?
So the question is about these additional terms in the Hamiltonian when you project into the basis of localized orbitals, right? So here you just talked about the T and U terms. While last time you said they're also going to be activated hopping terms and possibly longer range interactions and so on. I mean, now you didn't mention them, but
yes,
think
okay.
Important, and if so, how important are they?
Yes, and well, I guess, yeah, I mean, people are arguing about it. I mean, how far you, I mean, we have mostly been focused on sort of long-range Hubbard parameters, and that's sort of the bet we have made, but then other people are focusing on these, let's say, you mentioned the electron-assisted hopping term, that sort of Pacogenia has been proposing to be key to the physics and of this material. from what I understand, Alan MacDonald is sort of trying to debunk Paco Guinea's approaches. So I mean, you know, it's not settled, and yes. So I mean, there's no ultimate answer to this question.
Okay, thanks.
I mean, we're obviously in the process of broadening our looking at these terms, and but part of the, you know, I mean, my talk was basically anti-historical, because we did the normal state later than the broken symmetry states. And I can sort of see that a lot of people in the community are sort of abandoning these, you know, emergent Wannier approaches, and in favor of going to the microscopics, in favor of sort of truly sort of, you know, atomistic models, because of these sort of many problems that Wannier functions have. So I think there's a tendency, and we're all sort of also doing that, to sort of, you know, truly do microscopic calculations where you sort of just bypass all of these problems.
Right. Okay. Thank you.
So there's a question from Henry Sheehy. Would you like to ask your question, Henry?
Hi, Johan. Thank you for your talk. I have some questions that I would have saved for the student talk. They're probably a bit basic, but I was interested in how you were doping with electrons, and you didn't dope with impurities. I wondered if you'd considered that.
Yeah, so we dope. How do we dope with electrons? So we, you mean, for example, in the Hartree calculations that we do?
Yeah, and why did you choose to dope with electrons rather than impurities?
So this is because the doping in the experiment is not through impurities. It's not chemical doping like in the case of the cuprates. It's sort of electric field doping, when electric field is applied between an electron reservoir to push electrons from the gate electrode into the twisted bilayer. That of course has the advantage that you don't introduce any complications associated with the presence of impurities. So it's a much cleaner system. There are, of course, still impurities. You know, twisted bilayer graphene is a relatively clean system. It always depends on your point of reference. So I think there's impurities coming, for example, from the dielectric substrate material. You can have charged impurities in the dielectric substrate material that then scatter electrons in the twisted bilayer. Now, I think what is a very interesting probability is to try to sort of not view these impurities and adsorbates sort of as sort of things that are sort of random, but that you consciously put them, right? So you can try to adsorb, you can try to you know, change the properties of twisted bilayer graphene by sort of, you know, putting impurities in certain places. And there's a lot of reason to believe that this is an interesting route, because of the sort of you know, inhomogeneous structure of the material. There will be sort of preferred adsorption sites, and you can think that there might be sort of molecular superstructures that you can create on this material. And there's a couple of people already thinking in that direction, that, you know, you actually consciously put adsorbates or intercalants into this material to tune and change the electric properties.
And do you have some idea how that might affect the tunneling spectrum?
Yeah, I do have some ideas. So, for example, I mean, we're currently working on the properties of charged impurities. So you can, you know, if let's say if you put lithium atoms on graphene, they'll tend to donate an electron to the graphene, and you'll have a positively charged impurity. And for example, in case of graphene, it's very well understood both experimentally and theoretically how that will affect the tunneling spectrum. And we're currently trying to work out how similar or dissimilar that is for twisted bilayer graphene.
Okay. Can you give me a reference for that graphene paper?
So there's work by Leonid Levitov, the theory work, and the experimental work is there's a science and nature physics paper by the group of Mike Cromie in Berkeley.
Thanks very much.
But if you send me an email, I can send you the papers.
Okay, we have sent two with a question, and then there are one or two questions in the chat.
Yeah, hey.
Sent two.
Just wanted to comment on this exchange with Gunnar Moller. I missed a part of your talk, so I'm not sure if you addressed this before. But in this system, the bands are topological. So this entire question of 1 year and so on, and lattice models, exactly what range of hopping, those things are all sort of a dangerous route to go theoretically. Right? So so I don't know if you addressed that in your talk, but
yeah, so we had long discussions on Monday about Wannier functions, and yes, as I said. I think a lot of people are sort of moving to true microscopics because of the difficulties associated with Wannier functions.
So, what is true microscopic?
I mean, like I presented for my in the normal state calculations, you just take all the degrees of freedom, let's say all pz orbitals, into account. You don't try to develop a sort of effective description. You just do a truly microscopic calculation that doesn't throw out any high energy degrees of freedom.
Yeah, I see. So, I mean, one could do that, or one could just work with the band structure on the block wave functions and work with interactions in momentum space.
Sure, yeah.
Right. But still work within the low energy band structure, not keep all the higher remote bands.
Sure. Yeah, okay, yes, certainly you can just work in K-space. I mean, I guess the point is, the reason why I guess people like Wannier functions, and then this is what I discussed on Monday, is basically a lot of the strong correlation methods, if you think about sort of things like DMFT or, quantum Monte Carlo, a lot of these strong correlation methods are written in a real space basis, and they exploit locality, like DMFT in real space. So I think that's basically why initially there was a strong drive to develop a Wannier function, because a lot of people wanted to use these established strong correlation methods in the case of twisted bilayer graphene. But I think there's also a sort of a move to sort of K-space methods or microscopics.
Yeah, in fact, the inability of to use the standard DMFT or other such methods is perhaps what makes this even more interesting.
Yeah, I agree.
All right.
Okay. Question for a while now from Ajit Kumar in the chat. Is there any effect on magnetic behavior due to interlayer exchanges?
That's a good question. And the answer is, I don't know. I mean, we're currently doing basically these mean field calculations on the Hubbard level. So yeah, I mean, hopefully I can answer this question next year if you still invite me back. I mean, what I will say is that there is a question. I mean, what I think is a very interesting point is this question of emergence versus inheritance, which this sort of touches upon. So there's sort of two camps, and one says sort of, if you start with the untwisted bilayer, you already have a very interesting system that shows strong correlation physics. And if you twist that, basically, you modify the existing correlations, right? And so this is sort of the view of inheritance, that your parent system, the untwisted bilayer, already has strong correlations, and then the twisted descendant has the same correlations but modified. And then the other view is the sort of emergent view, that when you look at the two individual graphene sheets, they are sort of relatively boring from a strong correlation point of view. And if you put them together, if you bring these two sheets together at the magic angle, all of a sudden you have you have something special. So that point of view, you say there's something completely new emergent that wasn't in the constituent materials. And well, I think that's sort of an interesting question that also relates to how you think about this material. But yeah, that's all I can say. Sorry.
Okay, another question. Well, this is from Sam Carr. Well, he's wondering, because these are 2D superconductivity, do they see various VKT kind of physics?
Yeah, I do think this is seen. Yeah, I mean, again, I wouldn't pretend to be a superconductivity expert, so but I do think these words are being mentioned.
Sam, do you have any follow-up on this?
No, I was just wondering, like, most of the 2D superconductivity we know is actually layered, so the materials are sort of 2D, but the superconductivity is 3D. I can't personally think of another example of a true 2D superconductor. So,
or superfluids.
Yeah, well, superfluids, thin film helium is, I guess, the closest analog.
Yes, and yeah, so I guess on Monday we already discussed, I mean, discussions around misinterpretations of superconductivity, where basically experimentalists reported superconductivity, for example, in twisted TMDs, but there's no growing consent that actually it's not true superconductivity.
Yeah, well,
so,
I think purists would argue that no superconductivity in 2D is true superconductivity, but I mean, there's always a question of length scales. So.
Okay, I take your point, yes.
So I think we don't really have many other opportunities to see. And I've just not followed the field very well. I just wondered how much. But I can look as well as you.
Unfortunately, it's really not my area of specialty, these kind of things. So,
yeah, no. Thanks.
So another question from Yujin Zhang. Basically, do the upper layer PZ orbital and lower layer PZ orbital form a chemical bond?
No. So it's I mean it's thought to be a van der Waals material. So the bonding between the two is thought to be van der Waals bonding, so not the covalent bond.
And now we have a hands up from Daniel Munoz Segovia. Can you ask your question, Daniel?
Yeah, hello, can you hear me?
Yes.
Okay, so thank you for a nice talk. It was very interesting. And maybe it's a very naive question, but as far as I understood in the first part of the talk, you had a Hartree potential. Have you thought about the effects of the Fock term in this model?
Yes. So we're thinking about it. Yes, I mean Fock is a little harder than Hartree, just numerically. There are a couple of works that take into Fock exchange into account. For example, at the continuum level. So there's two types of Fock exchange, right? So there's kind of an atomic exchange, short range, and then there's sort of a long range exchange interaction between sort of these MOIRE orbitals. So there's the story is complicated because of these two different, what I would call types of exchange interactions, atomic and MOIRE. And one thing I'm wondering is, you know, what's the interplay between these two different types? Now, so the atomic exchange is something that we're currently studying, sort of in terms of like just an atomistic DFT plus U or Hartree plus U theory. And then the sort of MOIRE exchange is something that people have studied with the continuum model. So names are sort of Al McDonald, Paco Guinea. So the consensus is that the MOIRE exchange is weak, but it is something, and so compared to the Hartree, it's a small term, but it's something that can be, even though it's small, it can be responsible for phase transitions, magnetic phase transitions.
Okay.
Okay, I don't see any more hands nor in the chat. Is that true? Yes. So, and we're roughly out of time now. So let's thank Johannes again for a great talk. And this is the end of today's talks. So we start in about 10 minutes time for the student session. Is that right?
That's correct.
Okay. And who is going to be the chair of the student session?
Walker.
Ah, okay, excellent.
Hi.